Hi everyone, this is Luis Silvera and I welcome you to the Cybersecurity and Deep Learning Workshop. First of all, a little bit about me. I'm a computer science graduate master student with concentration on data science. I work at a research lab here at UTSA called Security and Autonomous Lab as a research assistant. And I work mostly on two research projects. The first one deals with detecting threats using logs from the systems. We use a transformer model architecture and we made it decentralized federated, which essentially means we learn from multiple computers separately and we combine all that learning into one model that can then be used by our computers. Then the second project is SIGLogs. Basically, it's kind of the same idea, but instead here we're working with network data. And that changes how we process the data and the kind of model we're looking to use. And second of all, I have an internship. I'm an intern at Idaho National Lab. There we do cyber threat intelligence. And for that, we use relational graphs, which is a way to represent an attack and how to mitigate it. For instance, you can think of an attack having nodes. On a graph you have nodes and connection edges. We can think of having a node that is a malware, and then we have indicators of compromise. We have actors, which are the ones causing or deploying this malware or attacks. And then we have mitigations, which is courses of actions. And that's basically how we can use cyber threat intelligence. And then we also work on malware analysis using machine learning techniques. For that, we analyze what is it, executable, binary files, anything that is a malware, we put in through machine learning. We want to find anything new on the malware, improvements. We want to analyze if there's similarity between malwares. And that's mostly focused on ICS. That's what Idaho National Lab focuses on, which ICS stands for Industrial Control Systems. And my interests lie within cybersecurity, machine learning, deep learning, and natural language processing. I'll cover in a bit what those essentially mean. So first of all, before we get in, how can we use deep learning for cybersecurity? Let me make it clear of what is deep learning. There's a lot of interchangeable use between deep learning, AI, and machine learning. And to put it on a clear perspective, you can think of AI as a way to have a superset that covers all this. AI essentially is just any kind of computation that simulates or tries to imitate intelligence. For instance, we have those recommendation systems, robotics, language processing, probabilistic reasoning, expert systems, and then what we focus on now is machine learning, which has been the most recent trend, growing exponentially. Machine learning is a type of AI that uses learning to simulate intelligence. In this case, we have multiple machine learning techniques. We have decision trees, reinforcement learning, clustering, regression, the artificial neural networks, and Bayesian models. Deep learning falls within the artificial neural network. That's what we're using, neural networks. And then even within that neural network deep learning, we have other architectures that we use, which can be convolutional, recurrent, or multi-layered. Essentially, a neural network is one neural network with one layer, and if you add another layer, that becomes deep learning to just make the neural networks deeper. So let's show how it actually looks, the difference between neural network and deep learning. You can see here in the neural network, which is have an input layer, which is where the data goes, hidden layer, which is where the learning happens, and then the output layer, which is the prediction or classification, whatever you use the neural network for. In the deep learning, we have the same structure. Instead, in the middle, we have more networks, which essentially makes it a deep neural network. Now, what are applications for this? The success stories have been NLP, natural language processing, and computer vision. Here we have some examples. In computer vision, this is a Tesla um, image of what they actually happen behind the scenes. And this is called object recognition. Computer vision deals with anything that uses AI, but mostly deep learning, to recognize any kind of images. And in this case, obviously the car is recognizing other cars. You can see also here that it's recognizing a lane and pedestrians, and even what kind of car is it, a minivan, a car, a truck. That is a computer vision. Language, natural language processing, it's just understanding the human language in general. In which case we have Alexa and Google Home, both that which you can just speak and it will understand you, even if different accents, different languages. So that's kind of where this is popular applications going on. These two actually, NLP and computer vision, have been what's moving deep learning to the edge. Is actually pushing the limits. That's what's bringing the state-of-the-art models, and that's mostly what most of other fields grab the ideas or architectures to apply. In my case, I mostly use NLP because I want to use sequential models. I want to use models that care about a sequence, what's going to happen next, and that's mostly used on NLP. An example of NLP using that is just like you texting. It kind of predicts or want to suggest to you what's the next word you want to type. So that's kind of a sequence. It cares about what's next. And that can also be used in computer vision, but vision is mostly focused on detection as objects. And then what about cybersecurity? So naturally, deep learning has gained a lot of momentum. It's very popular, trending, is a hot area. And for cybersecurity, we have some applications. So most popular ones are intrusion detections and prevention systems, which is what I mostly worked on. You want to use artificial intelligence to detect if an intrusion has happened, or maybe even predict it so it doesn't happen. You can also use it for dealing malware. The example I told you about how we use machine learning to learn about how malware works and the structure of it. We also have spam and social engineering detection. That's a typical example. You can use deep learning or any kind of AI actually to detect if an email is a spam or not, which Google does that already. If you see something on your inbox and then you don't find the email and then you see it on the junk or spam inbox, that could probably be Google thinking that is spam. Of course, some mistakes, sometimes it's not, sometimes it just look like it, but that's Google using that AI to detect the spam. And then we have network traffic analysis, which is what I've been working on, using a network data to see if there's some kind of intrusion going on. In this case, to make it practical and to have something to work on hands-on, I'll be using credit card fraud detection using deep learning, in which I believe most of us relate. We have a credit card and we usually take care of it. We don't give our PIN number to anyone. We don't just hand it out. We don't give our information. But even then, you're still vulnerable to have a fraud. Someone suddenly uses your credit card, you don't know how. And you just see some charges to your credit card and you don't remember doing them. You actually never did it. And then you're wondering, where does this happen? Who got it? And then you contact your bank and take care of that. But we usually want to detect that before it happens, or actually if it happens, the bank wants to know first and stop it, which usually does happen. For instance, if you suddenly move to another country and they see that you're using your credit card, usually your bank notifies you like, oh, is this you, the one using the credit card? They want to make sure that someone just didn't steal the information and using your credit card. Now, what I'll go over to tackle this problem, first of all, I'll describe the problem, the challenges to working with this kind of fraud, trying to detect it, how we can use machine learning, how it's being used, what we call exploratory data analysis and data preprocessing. Both of those come from data science. Basically, anytime you're working with data, you want to do this to make sure that you're working with the right data, and that is actually gonna produce good results. What you feed to the machine learning is what's gonna give you back. If you give good data, good results; bad data, bad results. As for the deep learning, I'll use what's called temporal convolutional network autoencoders. Don't worry, I'll cover that little by little. I will just throw that whole model at you. And then I'll go over the results. What is it that we were able to achieve through all these steps? Well, first of all, let's go over what the problem is. What is it that we're trying to do actually with the deep learning? A little bit of background of what is the magnitude of this cybersecurity problem, which is global fraud losses of 2020. It's $28.65 billion. That's reported by Nelson. You can see a huge amount of money being lost right there. And then also, this has not only consequences, say, to an individual, which does happen. It actually happens also to industry, corporations, and governments. So this is within the interest of many organizations to detect this. And it is important to detect the credit card fraudulent transactions, which happens a lot of times is that people don't notice that they're using the credit card. So for instance, if you don't check your credit card usage, there might be a little bit of money being used without you noticing, which actually is part of the way they work in fraudulent credit card transactions. They want to make it look like it's genuine, so you don't suspect, neither does the bank, any little purchase, and the bank will notice there's not much amount being used, and obviously you may just think, oh well, I think I bought that day, I'm not sure, but it's okay. But the problem gets bigger as they actually have your information and they keep continuing the use of your credit card. And then this fraud detection belongs to a class of problem that's bigger, which is anomaly detection, which I explained a little bit of it before, but it basically means to detect any exceptional, unexpected event within the data set. In our case, a fraudulent transaction. And this is a challenge. A lot of times, like I mentioned, a transaction can look just like a normal one. So to detect, oh, it's a fraudulent one, within millions of cases of a good normal transaction becomes a challenge. And that's what I'll cover right now. What are the challenges when trying to detect a fraud? Now, first of all, fraudulent behavior is dynamic. So they look like good ones. And so we're never sure how is it going to look. As we know in cybersecurity, any attack, the attacker gets discovered, or they discover the malware, or the attack patterns. What they do is they modify it to avoid detection next time. So obviously this is a challenge in which maybe we learn how the fraudulent transaction looks before, but they may make it better in a way that is hard for us to detect. And that's why we need to be prepared for all possible unknown forms. And this is very useful for AI, in which it can adapt to different kind of attacks. And then also the data set had imbalance. Of course, if we have many transactions, we use a credit card all the time, we have a lot of normal transactions, and then we just have most of us don't have any fraudulent. So getting data of, like, this is an example of fraud, is hard. And even more when you're trying to make a neural network or a machine learning model to learn it, because we're actually interested in learning how the fraud looks, but most of the transactions are normal. And this creates a problem. Your neural network will probably learn how to classify a good normal transaction, which is great, but we're more interested in actually what is a fraud. And this brings also another issue, which is a metric. How do we know if it's a good model or not? Naturally, we would always use in machine learning or deep learning in general accuracy, which is usually, okay, how many were good, how many were bad, did you detect them good? For instance, say cat and dog, how many times did you say that it was a dog correctly, how many times did you say it was a cat? And that's kind of always the trend, the use case that we have for accuracy. We just want to know how good is it at classifying or predicting. And in this case, it's not that useful. It is, but consider a data set with, imagine 99% of the data being a normal transaction and only 1% being fraudulent. If the machine learning model classifies all the normal ones as normal and even the fraudulent ones, that means it got 99% of the classifications correct. So that's obviously not what we want. I mean, it actually missed all the fraudulent ones. It didn't detect the fraud. So we can see how the metric is very important. So we have an actual good metric to, is it the model doing good or not? We want to actually have really focus on the 1% fraudulent. So I'll go over some of the traditional machine learning techniques. So I went over how machine learning has different fields and not just deep learning. First of all, we'll go over previous methods that we use for fraud detection, which we call usually traditional machine learning techniques. So first of all, we have a clustering, and then here what we can see is transactions and the purchase in dollars with this week, and then the average purchase per week. And we can see a cluster clearly around that green circle, and that's what we consider normal. So we can say anything that is within there can be seen as a normal transaction. And possible fraud, something that is outside, in that case the blue triangle you can see is way outside, so that could probably be a fraud. For this we have methods such as PRINCA, which is principal component analysis. We have clustering with k-means or k-neighbors, nearest neighbors. And this is one technique, clustering technique. So we want to have suspicious anyone who doesn't behave like the rest. Then we have rule-based methods. This is essentially having rules of what is a common transaction and what is a fraud-based transaction. And these rules are created by domain experts. They're the ones who specialize on this. So there you can see a little bit of human involvement in this, actually experts to see what is it that makes a transaction fraud. And here have some examples: over the limit, high rates, stolen car. Obviously if you know it's a stolen car, you want to say right away anything after transaction after reporting a stolen car should be denied. And a limitation of this is that you need rules. So obviously rules are set, they don't change. You can add more rules, but then you have this huge amount of rules and you gotta pass all of them. And you can think of a fraud that doesn't fit within any of those rules would actually be a proof. So that's another traditional machine learning method. And a third one will be the decision tree. Now this is based on, you can think of as a tree with nodes and then basically a decision making is yes or no. So for instance, if you have the amount that is being on the transaction, if it's less than 50,000, then you look at, okay, what are the number of locations that were used at the same time? Or if it's more than 50,000, what is the IP at the address customer? And this tree basically just follows you through a path into whether it's a fraud transaction or not. And you have yes or no, you have probabilities of how much is it that is a fraud or not. These are the traditional machine learning techniques. Now I'll go over the actual deep learning. So deep learning, as I previously mentioned, it's just neural networks with more hidden layers. And what we want is different layers, which are this hidden layer 1, 2, 3, 4, to learn about the data. We want them to see what is it that makes a fraud or not. And this is what neural networks are useful for. They do the learning by themselves, and they learn by giving it a lot of data. It needs a lot of data to actually learn from examples. First of all, the data is fed into this input layer, and we pass that data through activation layers, which goes beyond this workshop. Neural networks basically use activation layers with weights and biases to pass on the learning, and they adjust weights. And what we want is through these layers, it should at the end predict, or in this case classify, is it a fraud or not. In this example we have 4, but we can have the output layer to be as many as we want. In our case that would be 2, yes or no. And at the end what we want is a probability. What is the probability that is a fraud? What is the probability that is not? And what is gonna make the probability work is this hidden layers. And it goes through iteration. So basically how this deep learning works is we put data in, and then through the network it tries to predict what is classified, what is a fraud or not. Then we have an error, which is how bad did the network do, and we back propagate, which is basically telling the hidden layers, okay, this is how big the error was, let's adjust to have a better prediction next time. And they adjust the network, and then again the data gets fed into the new network. And with the new weights, which is what we use to learn in the neural networks, we try to classify again, is it a fraud or not? And we again calculate the error, the loss, how bad did the neural network do? And we again back propagate, we tell each layer how much they should adjust their weights to have a better classification next time. And this is just how it goes. We just keep feeding the data, trying to classify. The network classifies, we see how bad we did. We tell the layers, okay, this is how much we need to adjust. We do it again, and it just keeps going until we have the results we desire. So the model improves over every iteration, and that's what we're aiming at. We just want the neural network to do its job, learn what is it that makes it fraud or not. The learning happens within these hidden layers. Hope that makes it clear. If not, please feel free to ask me how does this work. If you want to go more specifics about what is loss function, the activation, maybe the propagation, which basically uses calculus and gradients, and then also this goes beyond this workshop. I assume you have a little bit of at least knowledge on neural networks, and in this case deep learning, but please feel free to ask any questions you have. And then ideally we want each layer to have a function, like we want this one to identify the customer, learn about the amount of transaction, learn about the location, learn about the frequency of transactions. This is what we want. So we want the neural network to learn what makes a fraud or not fraud. Now let's get started. We have a data set of fraud transactions and normal transactions. This data set was made available by UBL Machine Learning Group. In this data set, I'll provide you a link. The link may be in the notebook. I think I put it there. And then also you can download it, so you can actually use it on the Google Colab. Google Colab is software by Google, a web notebook that you don't need any software to install into your computer. You can just open it online and use it. And transactions made by credit card are in this data set from September 2013. We have the transactions from 2 days, basically 2 days of what it was 492 frauds, and there were actually a total of 284,000 transactions. So you can see what I was talking about. We have only 400 frauds, and there's almost 250,000 transactions, or more than 250,000. And this, as I mentioned, is highly unbalanced. The positive class, which is what we want to detect, the fraud, is 172% of all transactions, and that's obviously a challenge. How does the data look? So we have 30 features, which is composed of 28 principal components of extracted features, V1 to 128. I'll briefly explain what that is right now. We have what is the time of the transaction, and then we also have the first transaction in the data set, and then the amount paid for each transaction. The data set has labels, so basically if you see a 1, that's a fraud, fraudulent transaction. If you see a 0, that means it was a normal one. No issue with that one. And so what I was mentioning, V1 to V28, is that we have these features actually, due to confidentiality issues, we don't know how they came up to be. We just know they use PCA to get those variables, those features. And that's obviously because they don't want to give out people's information. But this information is still very useful. It's just reduced information. And that's what we'll be using. You have an example of how this can look in Google Colab. If you use the head function with your data frame, you can just see that values, we're not exactly sure what it is, but we know they'll be useful because they were provided to us by the dataset machine learning group. Here's the amount of money that was used on the transaction, and here's fraud or not. Zeros means they're not fraud. And here actually all the columns, all the information we have. Time, V1 to V28, the amount, and the class. And actually I can show you that in the notebook. Oh, so here it is, where you can get the data from. I will go ahead and share this notebook with you, so don't worry, you can actually get it and download the data yourself. Here we have imports of what we'll be using, and I'll be back and forward between the notebook and the presentation. I want to make this so you can not only learn about it, but actually get on it, work on it. And here we have the imports. In this case, I have it to my drive, and you can also do that easily. Say once you download a file from the links I provide, it can be from Kaggle. If you don't have that accounts, and you can just get it from Google Drive, which I shared. You can put here, upload the file, and once you upload it, it will appear here. Once you download it, you can put it here. And then what you can do is just put copy path. When you put copy path, you can paste it in here, and that'll be it. That will let you import that data. If you have any questions or issues, let me know in the chat, and I'll go ahead and address that. So with head, you can have actually the data, you can see it, and then you have the columns, which is what is it that the data represents. So we have distribution imbalance. This is just a little graph of how imbalanced this data is. You can see a lot of normal transactions and very little credit card fraud transactions. And here we have a visualization. I use PCA. What we do is reduce the features from 30 to 3. So we basically have 3 variables that represent the whole data set. And you can see 2 clusters, and you would think, well, that's easy. These are the normal ones, these are the frauds. However, it turns out that's not that easy. You can see these yellow dots, those are actually the frauds. So now you see the challenge in trying to detect fraud within all this data. So for this, to tackle this issue, we use subsampling, which is basically taking, making the imbalanced data set more balanced. In our case, we're going to take, instead of the 280,000 cases, just 1,500 cases. And why we want to do this, we want to avoid overfitting, which is like the model, learning what is a good transaction but not learning what is a fraud at all. And we subsample 25-25 ratio, which what we want is 25 of it to be fraud and 75 not to be. And that's why we get around 1,500, because we had around 500 frauds. We want our pattern to determine whether a transaction is fraud or not. We want to help it do that. And then we create just a new subset of 1,500. And now you can see a visualization of how this will look. It's 1,500 and around 500, so we can make it a bit less unbalanced. We also don't want to make it totally balanced, like 50-50, because that's not much of a real world case scenario. You don't just have fraud transactions happening half of the time, so we also want to kind of make it a little bit realistic. Now if we subsample, look what happens. We actually get a bit of more separation. Now we have the purple ones being here and the yellow ones, which are the frauds over here. So that's a benefit of subsampling, basically getting a little bit of data out there. Now that we covered the data preprocessing steps, we can start working on the deep neural network. First of all, let's go over a single layer neural network. And what we have here is the data, the input. This is called the input layer, and here we put, for instance, time, v1, v2, all the way to amounts. Those are the features that we have. This is where the learning happens in the hidden layer, and here we're gonna have weights. These weights are gonna be learned, adjusted to have a better prediction here at the end. And what happens here is basically a multiplication between the input and the weights, and we add a little bit of bias, and that's beyond this workshop, but you can go ahead and look it up. It's common standard to have this bias. And what we do is we add the operation of all of them to obtain the weights, for instance, in this first node. And then we repeat that same steps with another set of weights, and that will be for our final predictions. And then at the end here, what we're gonna have is the results of the classification. And this is what we do just to send the data to try to predict, or in this case, classify what is the actual answer, if it's fraud or not fraud in this case. Now we can think of the prediction here being 0.01 and the actual one is 1. In our case, what we do is we go to the closest, the probability. For instance, if we have here 0.1, that means it was predicting a 0, which the answer was actually a 1. In this case, you can think of it like it predicted it wasn't a fraud when actually it was. And that's the point of this deep neural network. Well, in this case, it's just a single one. And we need a loss function, which is a way to tell the neural network how bad it did. And I'll cover that here. This is a cost entropy loss, and it's usually just to measure the loss in the models that have probability between 1 and 0. So you can think of it 0.05 going on above means fraud, 0.05 going down, non-fraud. And we're going to use that to measure how good our model did. Here it is, an example of, imagine this is the data and we're trying to predict or classify what is it. If we get a 0.1, that means the model said it was a 0. 0.0, that means the model said it was a 1, which is incorrect. And that's just how we go. We go measuring how many of them did it get wrong or right. And this is just going forward what I talked to you about right now. And now imagine that same process, but with many layers, many nodes, many more nodes. And you predicting, again, you just saying at the end, is it a fraud or not? In this case, we have 4, but in our case, we'll have 1. And we have, how does it learn? How does it learn from the error, the loss, how much it should adjust? We have what's called back propagation. So after the error, the loss, we go backwards and we tell each layer how much it should adjust its weights to have a better classification next time. And this is an iterative method. So think of it as it classifies, it gets a little bit wrong, like it's not a perfect model. We measure that loss with this cost entropy loss, and then we go backwards. We tell each layer how much to adjust its weights. If you remember, the weights are these connections, and these are these ones. This is what we're actually modifying to have better classifications, and we just keep iterating that way until we get the results we're looking for. And our goal is to this neural network learn to identify features. What is it that makes it a fraud or not fraud? For instance, some layers could learn what is the identity of the customers, which in this case we don't know actually. We do know the amount of the transaction, maybe the location, and then we also have frequency of transactions. That's what we want to have, something that can learn those representations. An important part of neural network are activation functions, and we use them for learning and for the final output layer as well. So for instance, take this data set, think of it as green being non-fraud and blue being fraud. And in this case, if we get a transaction and it's on the blue side, you would most likely put it as a fraud. If it's on the green side, then you say it's not, it's a normal one. But in the real world, we have stuff like this, which it looks alike and it's actually within the same data. So frauds, it behaves just like what maybe non-fraud would be. And nonlinear layers allow us to have this line, make a model that can make this line and identify the frauds even within normal transactions. That's for learning. Now for the final output, what we use here is the sigmoid function. It just gives you an output of from 0 to 1. And in our case, 0.5 to 0, it's just not a fraud. 0.5 to 1 means it's a fraud. And this is what we'll use, the nonlinear layers for our deep neural network. And here where we have it, we created with this sequential function from Keras. And we first put here in dimension of the data, which is 30, because we know we have 30 features. Amounts, V28 to V1, that's 28. And time, that's another one, so that's 30. And then we have units, which are the nodes in the neural network. You can change this. Too little, you get not much results, or too big, you also get low results. It's not like the more nodes, the better it does. There's a sweet spot, and you just modify it to see what gives you better results. And we have the activation layer for learning, in this case ReLU, which is rectified linear unit. This is conventionally used, it's an easy one, and applies to most methods, in this case for classification. And we have 3 hidden layers, and here I have 24, 20, and 24. You can add more layers, you can take away more layers, you can add more nodes or less nodes. And then at the end we have again the one with the sigmoid function, which is going to give me value between 0 and 1. And you see we only have one node because we don't need another one. Which this one, if it just gives us below 0.5, the model is trying to say that it's a non-fraud. If it gives us something above 0.5, that's a fraud. And here is just a summary. If you use the summary function, it can tell you what is going on, what are the data, and these are the parameters. How many weights are being connected? You remember from the 30, and we have 24. We just have those connections happening, and those are all the weights, which in this case we call parameters. And to train it, we have this compile. Is where we tell it the optimizer, which is just how it's going to learn. Atom is an adaptive learner, and this is the one mostly used. And then we have the loss binary cost entropy, because we only have 2 values, 0 and 1, so we can have that loss measure. If it's set a 1 and it was a 0, then we can say that's wrong, and then vice versa. And then we have the accuracy, which is what we're trying to see. And we have fit. Fit is what actually runs the test. And we have training data, meaning we're just going to learn from this data. And we have epochs, which is how many times are we going to iterate over the data. And to validate, like to see the actual results of the model without learning, we tested with these X and Y tests, which we did the splitting before. And verbose one just basically means show me what's going on. Here we can see the accuracy, how it does in every round. So in every epochs, that's how we call it. And here we can see that it's actually getting better. This is the training in blue, and validation is where the test happens. And you can see how it's going up, the training, and the validation is good. I mean, it's 97%. But there's a point in which training is doing good, but validation is not doing good anymore. Instead, the accuracy stays steady and it's actually going down. That's what we call refeeding, and it becomes more clear over here where the actual validation loss is starting to go up. Loss is how bad the neural network did, and we want that one to keep going low, just like training is. What you can do here is modify the neural network, more layers, less layers, change activation functions, include more rounds, see if that happens, which in this case won't, because I mean 10 seems to be the sweet spot. 10 rounds will give you the best results. for this data. But if you remember, I mentioned before, accuracy is not that good for detecting frauds or any kind of intrusion in cybersecurity. What we want to focus on is the actual attacks, which in this case is a fraud. So for that, we have the true positives and false negative, false positive, true negative. True positive means there was a fraud and he detected it. False negative, there was one, but the model did not detect it. Usually it's not what we want. False positive, it's okay. It's a normal transaction, but the model detects it fraud. We also don't want those, but that's better than having a fraud and not detecting it. And then we have true negative, which is there's no fraud and the model did not alert. And in that case, it's actually here in the code. It's this confusion matrix, that's how we call it. And here we have the fraud, it detected 78. And here we have the normals, it said 308 were normal. But here's the actual, what it was actually, in this case of frauds, it was actually a fraud and it said normal 6 times, meaning the model classified this incorrectly. And then again here, the actual one was a normal, but the model thought it was a fraud. So that's what we use to know how good we did in detecting frauds. And we have these measures, precision, recall, F1, score. And we use those because those give us a better idea of how the true positive and true negative results help in detecting frauds. For instance, here are the definitions. These here are the basic functions. But here's a visualization of what we're trying to focus on. True positives are the frauds. So the precision is just how many fraud did it detect overall, the true positive and positives. And then we have recall, how many did it detect from the false negatives and true positives. So here we're just focusing on the frauds to see how good it did with that. And F1 score is just the mean of those two. And here we have the scores, and in this case all of them are above 90, so that's good. That's what we want, a good recall and F score and precision. That was good results with the deep learning neural network, and now we can briefly have a quick introduction to convolutional neural networks, which is a type of deep neural network which is mostly used for image processing. And you can see it on computer vision, anything that has to do with images. But it can also be used for classification, which is our case. The idea with this convolutional neural network is to go through this matrix and go patch by patch, which is this smaller matrix. And then from those, we can learn features. And we go like this, we go side by side, we have a sliding window. And I'll explain what would this be right now. In our data, we can say this is the data, the 30 features going below, which is time, and then the V1 to V28, and then amounts. And this will be at time, say time 0, and then at 1 second after, this is the next feature, the next data. And then 2 seconds, this is the next one. And then you can see that every column is time as it passes by what is the transaction. And the idea of this is that we can grab information from our neighbors. So when we're trying to classify if it's a fraud or not, we can look at the previous transactions as well. And before the neural network, with the simple deep learning neural network, we will only have one column and that'll be it. From that, we have to decide if it's fraud or not. What this CNN gives advantage is that now we can look at every neighbor on the site. And you can see here we just slide window to the next one. Now, to do this, we have a convolution, which is the process of having a kernel, which is a smaller matrix that we mentioned. And we do an operation with the input data, the kernel, and then we get at the end one single number. This convolution is just a multiplication and then adding those multiplication into one value. And what this kernel is, they are the actual weights. So if you remember on the previous deep learning neural network, the connections were the weights, which was what learned and knew how to classify every transaction. Now we have more weights. We have, in this case, 9 weights because we have a 3x3. And like I mentioned, what we want is to learn features. We want to learn what makes it a fraud or not. And we have also max pooling, which is reducing the matrix. And pooling is basically a way to get from each, well, you decide the size, pooling size, one value. In this case, max pool is just max. You just get the highest value of it. In this case, 12, 30, 112, and 37. And that would just reduce the matrix into having the features, which is what we call map features, which is what helps the neural network make better classifications. And remember, the important part here is that it's actually looking at transactions before and after, so it can make a better classification. How do we add all those? We just have the input. We create a layer of convolutions, which is this essential thing, multiplication and adding those. And then from this, we create this matrix. From this matrix, we pull in this case, a max. And this is another neural network. The only difference is the functions you have inside each layer. So we have convolutions, pooling, and then we have a function called flattening. So these are matrices, and we cannot fit that into a neural network like this. So what we do, we just flatten it. We make it a vector with only one column in this case, and then we put that into a dense layer. You remember this one is what we had before, and this we fit it into here so we can make a final classification. Here it says 4, but in our case we just have 1. So before that, let me just go to the code and show you how this can be done with Keras. Now first, what I do is I modify the dimensions here, so I can have a matrix of 30 by 1593 or 1593. Instead of having just 30, now we have multiple ones. And how it works is, this is the time. I know time cannot be negative, but we normalize it, meaning we change the values to make it more fit for the model. And this is the next second, for say for an example. And these are all the features, and that matrix is the next second. And actually you can see here that that's what we had time originally. Originally we had time as 0, 1, 2, but we normalize it so we can, here you can see the change, so we can have values that are closer range. We don't want something saying 36,000 seconds. We want values between usually -1 and 1, but as close as we can get to that. And you can see here time, and then you can see the values are actually extended. So that's all it is. We have each column is just the next transaction, and fit that into the convolutional neural network. Now this one has a little bit of different functions. This is a filter, which is what is the output of that matrix. How big is it going to be? Kernel size, as we mentioned, like this is a 2x2, so we have 4 in total. And then we have the activation layer, again ReLU. The input dimension, so in this case is shape. I put the actual shape, so if you change it, it can actually adjust to it. Batch normalization is just another method to avoid overfitting, which I mentioned before. It goes beyond this workshop. And then we have max pool, which I show you, like we just get the highest value, in this case like 2x2. And dropout, this is another normalization trick. Instead of letting all the weights make a classification, we drop 0.2 of them, which is we try to make it learn with less data, and that's why we do this dropout. And we do the same thing, another convolutional and pooling layers. And here we actually increment the dropout. We have the flatten layer, which is what makes it one vector, and now instead of having a matrix, we only have one with 64. Again, an activation, dropout, and then 1 unit. Same thing, we have a sigmoid. If it's above 0.5, it's fraud. Below, it's not. Summary. Here's where we have what is going on. You can see these are matrices all along, and then when we flatten it, it gets into one long vector. And then we fit it into the linear layer. Has way more parameters than the deep neural network. It's a bit more complex architecture. Same learning rates with Atom. In the previous case, I didn't specify one, but this is also something you can modify. Same loss, accuracy, what we're trying to see. Same training. And again, we plot it. In this one, we actually get better results for validation than training. But what is important to note here is that we see that it's going up. So most likely, if we keep training, this will continue going on. You don't see that you saw previously in the deep neural network, that the loss of the validation was going up. We have an accuracy, which again I mentioned is not good of a measure, but you can see here that we actually have higher precision F1 and recalls than the deep neural network in general. It's pretty high actually. And the confusion matrix at the end just to see. Here we have a fraud that was no tagged as a fraud, but it was normal, and here we have a normal that was tracked. That was actually a fraud, but the model said it was normal. And these are just 2 deep learning neural networks that are fundamental if you're looking into how to apply this into any cybersecurity task. So in conclusion, we created a deep neural network and a CNN and Keras that classifies the data. We saw that it was easy, simple to use. You saw that it took not more than probably 10 lines of code for the deep neural network. And then for the CNN, it didn't even increase that much. And then also, once we have the model trained, we can just give it a new data, and it does the classification instantly. And that's also another advantage in trying to apply deep learning to cybersecurity. You get instant results. We have something called online models, which are models that are constantly running, which is probably what is deployed on companies that use deep learning for the cybersecurity. Instantly, it tells you if something's wrong. But we saw that we still had some frauds that were not detected, and that's something important to note. It's not perfect, and maybe we can fix this by actually using feature extraction, which is basically what is going on. And same thing for knowing what the data says. Maybe we knew what the V1 was, and maybe it was the country. We can make correlations saying, okay, because it was this country, this is why the model made that prediction. And that's a basic deep learning implementation for cybersecurity case of credit card fraud detection. Thank you for your attention, and I'll welcome any questions.